Hello, students. So, what we've just accomplished is proving one of the important results that you remember from calculus, the extreme value theorem, which tells you that continuous functions on compact sets can be maximized. Or I guess, depending on the path you followed, you may have just seen the proof that continuous functions on closed bounded intervals can be maximized. In this video, I want to reintroduce you to another of the results from calculus that you should remember, the intermediate value theorem. So let's just go ahead and remember what the IVT says. The intermediate value theorem, abbreviated IVT, says the following. Suppose that f from ab to r is a continuous function, where by ab there I mean a closed bounded interval. Let's let m be any number that satisfies either that f of a is less than or equal to m is less than or equal to f of b, or f of b is less than or equal to m is less than or equal to f of a. So either of those should be interpreted as saying m is between f of a and f of b. I just don't know whether f of a or f of b is bigger. Then there is some c between a and b which satisfies that f of c is equal to m. So the picture of what this theorem says is, let's suppose you have a continuous function and there's its graph over some bounded interval a, b. If you pick, so there's f of a, here is f of b, or rather I guess the y values are f of b. So if you pick some y value that's some other y value that's between those two y values, say that y value, so there's this y value m, what the intermediate value theorem says is that there must be some input between a and b where f of that input is equal to m. And from the way that I drew this picture, it seems like an obvious fact. If you have the picture of a graph, it starts below some dotted blue line, ends above that dotted blue line, then someone has to cross the dotted blue line. But the definition of continuous function doesn't have anything to do with you can graph them without picking up your pencil or anything silly like that. In fact, that's a really bad definition. So we'll need to come up with something a little bit better. We need a proof. Let's prove this theorem. Or maybe instead, now that we know what the theorem says, let's use the theorem to prove some things. And this is like a Calc 1 application. You can use this to prove that equations have solutions. So let's prove that this equation has a solution. X to the fourth plus x cubed plus x squared plus x is equal to 1. I claim that has a solution in the interval from 0 to 1. Well, let's go ahead and do it. Let's see. Take f of x equal to x to the fourth plus x cubed plus x squared plus x. I'm looking for a solution somewhere between 0 and 1. So let's see, is this function continuous on 0, 1? Yeah, it's continuous everywhere. Then f is continuous. It was a homework problem, in fact, that you guys did to check that every polynomial is continuous. F is continuous on 0, 1. And notice that's one of the hypotheses in the intermediate value theorem. You need a function that is continuous on a closed bounded interval. The next thing you need is a number m, which is between f of a and f of b. And that m is the output that we find an input that corresponds to. So it looks like we want to think about m equals 1. So let's think about m equals 1. Well, let's see. F of 0 is 0. Good, that's less than 1. Let's be hopeful and assume 1 will be less than f of 1. Well, by looking at f of 1, it looks like f of 1 is 1 to the fourth is 1 plus 1 cubed is 1 plus 1 squared is 1 plus 1. That's 4. Yeah, 1 is less than 4. So 1 is between f of 0 and f of 1. Thus, by the IVT, there is some c in that interval with f of c equals m. Next, let's do something that we've done in a few different ways in this class. Let's prove there exists a square root of 2. Let's show there exists a positive number, x, with x squared is equal to 2. Well, let's start off to the side. So I need an a and a b so that f of a is less than 2. Well, a squared is less than 2 is less than b squared. Well, let's see. 1 squared is 1 is less than 2. Good. 2 squared is 4 is bigger than 2. So let's use those. And it looks like we're also interested in f of x equal to x squared. So let's now actually just, I'll write something super similar to what was written in item 1. So let's take f of x to be x squared. Then f is continuous. And you'll notice off to the side that I found that the inputs of 1 and 2 would be useful. So in particular, I'll be interested that this is continuous on the interval from 1 to 2. It's continuous everywhere. It's a polynomial. Polynomials are continuous. Excuse me. But in particular, it's continuous on 1, 2. Then f is continuous on 1, 2. Moreover, f of 1 is equal to 1 is less than 2 is less than 4, and 4 happens to be equal to f of 2. Thus, by the IVT, let's see, the IVT does produce a number, a thing that gets called c, but we want a number x. I'll call it x. By the IVT, there is some x in 1, 2 with x squared equal to 2. Let's even put more words in. F of x equal to 2. Since x is in 1, 2, x is bigger than 0. So x is positive. Since f of x is equal to x squared, we have x squared equal to 2. Excuse me. Okay, I'm back. So let's use this to do something a little bit more abstract. So suppose that m bigger than or equal to 0 is any positive real number. Let's show that there exists a non-negative number x whose square is equal to m. And I'm even suggesting some bounds right here. Let's try using a equal to 0 and b equal to m plus 1. And let's actually start with this. So let's do that. So let's go ahead and let m be bigger than or equal to 0. Then let's think about m plus 1 quantity squared. So see, that will be m squared plus 2m plus 1. And let's throw away single pieces one at a time. So that will be bigger than just 2m, which in turn will be bigger than or equal to m. because m squared plus 1 is bigger than 0. Thus, you can erase m squared plus 1 and get something smaller. And 2m is bigger than or equal to m because m is bigger than or equal to 0. So using those two facts, we get this chain of inequalities. Now let's define the function we want to use. So I'm still interested in squaring. So let's use the same function. So let's take f of x to be the function x squared. Then f is continuous on the interval from 0 to m plus 1. Right, because it's continuous everywhere. It's a polynomial. Because 0 squared is equal to 0 is less than or equal to m, which we have found is less than m plus 1 squared, which is equal to f of m plus 1. So one thing I've decided that I don't like that I'm going to change. Instead of saying 0 squared there, what I care about is the fact that this is f of 0. So because we have that chain of inequalities, the IVT concludes that there is some x in 0, m plus 1 with f of x equals m, i.e. x squared equals m. So what did we just do? So let's just summarize this again. We just showed that every non-negative number has a square root, which is nice. So here's something that you'll do in homework, though there will be some discussion of it at the end of this note packet. Let f from R to R be a continuous function whose image is neither bounded above nor bounded below. I claim that this function f is onto. So if you have a continuous function defined on the whole real line, which has some places where it gets really big and some places where it gets really small, it could be a really complicated function, right? I'm thinking about a function that wiggles bigger and bigger. That function will be onto. So the proof, not of item 4, but the proof of the IVT, there's more than one. There's one proof which will appear as an extra credit that you'll do by constructing some sequences. This you'll think of by studying some sets. So you're going to study the set of all x's for which f of x is less than or equal to m. Let's go ahead and, let's even take this picture right here. Say on that domain with this choice of m. So the proof will proceed by studying the set of all x's for which f of x is strictly less than m. So let's do that. So this x value, so I'll trace out the bit of the graph where the y values are less than m. There they are. Something like that. So that means the bit of the graph that I want to study, the bit of the graph that I want, consists of, let's see, a little bit thicker and Okay, so let's draw it. So it starts here, then it starts going this way. We miss this endpoint. We exclude that endpoint. We carry on up to there. So there's that blue set that I just drew. So there's the set of all x's for which, so the thing that I just drew is the set of all x's for which f of x is less than m. The supremum of that set, let's call it C. So let's go ahead and go over here. It looks like the supremum of that set is right there. So there's the thing that I would want to call C. Let's see, does this x value appear to correspond to a y value that is exactly equal to m? Yeah, it looks like it. So it looks like that's what I want to study. I want to study the set of all x's where f of x is less than m. I want to take the supremum and try to show that f of the supremum is exactly equal to m. And here's going to be the trick. So if you look at C, if you look there, zoom in really close. If you look a little bit to the left of C, notice that's in the blue set. So this input will have f of x less than m. If I look a little bit to the right, I'll see something that's not in the blue set. That thing will have f of x bigger than or equal to m. So somehow continuity from there should force f of c to be equal to m, because these points will make it want to be less than m, these points will want to make it be bigger than m. It can't satisfy them both, but the best it can do is be equal to. So there's a sketch that's not a proof, and it was hardly readable even in that cartoon. But let's go through the actual proof. So let's let f from a to b to r be continuous. Without loss of generality, let's assume that f of a is less than or equal to m is less than or equal to f of b. Right, of course you can do that. Let's define u to be f inverse of negative infinity to m. So let's unravel what this set is. So this is equal to the set of all x's such that f of x is in negative infinity to m. Oh, but what does it mean to be in negative infinity to m? This is exactly the same as the set of all x's such that f of x less than or equal to m. So that's exactly the set we were talking about in the discussion before the proof. So let's study that set. Apparently I want to think about the supremum of that set and prove something about the supremum of that set. So let's do that. So in order to talk about the supremum, you need the set to be non-empty and bounded above. So let's prove that the set's non-empty. Well, one thing that we have by assumption is f of a is less than or equal to m. F of a is less than or equal to m by assumption, so that means that f of a is in the interval from negative infinity to m. So by the definition of preimage, that means that a is in f inverse of the interval from negative infinity to m, which is the set that we called u. So we just constructed an element of u, so u is non-empty. Okay, so what types of sets have suprema? Well, sets that are non-empty and bounded above. So let's see. F is a function from a comma b to r. So it has domain a comma b. So that means that the preimage must be contained in a comma b. That means that b is an upper bound on u. So that's a sloppy upper bound though, right? I'm just saying that this point right here is an upper bound. But that's good enough, right? You don't need to be optimal when you find an upper bound. We will be done. So let's let C be the supremum of u. I want to show that C is in the interval from A to B and f of C is equal to m. And one of those will be like pretty obvious, I think. Let's show that C is in the interval from A to B. And this will basically, yeah, it'll be fine. So what do we have right now? So why is C in the interval from A to B? So let's try to explore this kind of in scratch walk off to the side. I want to show that C is in A comma B. And remember, C is equal to the supremum of U. Let's think about what we even just did. So we've shown B is an upper bound for U. But C is the least upper bound. So that means C is less than or equal to B. Now we have also already checked that A is an element of U. If A is an element of U and C is an upper bound on U, that means that A is less than or equal to C. So I'll get A less than or equal to C, less than or equal to B. C is in A comma B. Very good. Now let's just put that into WODs. Why is C in the interval from A to B? So we've already seen that B is an upper bound on U. Since C is the supremum of U and B is an upper bound, we conclude that C is less than or equal to B. Very good. We have also already seen that A is in U. Since C is an upper bound on U, we then conclude that A is less than or equal to C. Thus, A less than or equal to C less than or equal to B, so C is in the interval from A to B. Nice, so check. Now we need to show that f of C is equal to m. We'll do that in two steps. We've followed this sort of proof technique in analysis a few times, and this is a really good proof technique to just generally be aware of. If you want to show an equality, try to just show two inequalities. So, first let's try to prove that f of C is less than or equal to m. But that's still too hard. Instead of trying to prove that on the nose, I'm going to try to prove that f of C is less than m plus epsilon for every epsilon bigger than 0, as we've seen in a previous homework. That will then imply that f of C is less than or equal to m. All right, so let's do that. So there's the thing that I'm going to try to prove. Let's try to prove that. Well, let's do it. So this function f is continuous at C. Well, I want to prove something is true for every epsilon, so I should start by considering any epsilon bigger than 0. This f is continuous. Well, continuity gives you a way of getting a delta out of an epsilon. Since f is continuous at C, it follows that there exists some delta bigger than 0, such that for all x in AB, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. Cool. All right. Well, let's see what that means. And maybe in order to motivate it, let's draw a little picture. So here's that point C. There I see f of C. So if I look epsilon above f of C, epsilon below f of C, then there exists some delta such that as long as the x values, sorry, that was muffled by a cat walking in front of my face. So that as long as I take an x value that's within a delta of C, the resulting y value will be within an epsilon of f of C. So there's the pictorial version of that. And I'm going to refer back to that picture a few times. So let's see, this number c is the supremum. It's the least upper bound. So let's think of it this way. Since this is the least upper bound, could this number possibly be an upper bound? No, it couldn't be. It's something less than c, which is the supremum. So that means there needs to exist something in here, some element of u. Oh wait, but remember what that means. That means that this y value has to be less than or equal to m. So let's take advantage of that. So using the reformulation of the supremum in terms of an arbitrary positive quantity, this time delta, there must exist some x in u such that c minus epsilon is not epsilon. C minus delta is less than this x value, which I'll go ahead and remind myself that that'll be less than or equal to c, because c is the supremum. And so why should this imply that the absolute value of x minus c is less than delta? Well, take a moment and do that on your own. It's well, no, I shouldn't do that. It is straightforward, but that means that I can do it on my own, right? So I'll get c minus delta less than x is less than or equal to c. That in turn is less than c plus delta. Out of that, we get minus delta is less than x minus c is less than delta. So, absolute value of x minus c is less than delta by properties of absolute value bars. Oh, wait. So, but then absolute value of x minus c is less than delta. That means absolute value of f of x minus f of c is less than epsilon by 3.1.3, which is right here. If the absolute value of x minus c is less than delta, then the absolute value of f of x minus f of c is less than epsilon. If I know absolute value of x minus c is less than delta, then I get absolute value of f of x minus f of c is less than epsilon. Cool. But remember, this x value is in u, which is the pre-image of negative infinity to m. So if x is in the pre-image of negative infinity to m, it follows that f of x is in negative infinity to m. And so what inequality do we get? We get the inequality that defines that half-infinite closed interval. So what do I have right now? I have right now f of x is less than or equal to m, and f of x minus f of c is less than epsilon. So I'll draw these vertically. I know that there's m, there's f of x, it's somewhere below m, and I know that if I go up by epsilon or down by epsilon, f of c will be somewhere in that golden range. Oh wait, but everything in that golden range is certainly less than m plus epsilon. So I believe it. Let's just now do it. And let's do it by unraveling this line right here. So let's see. Because absolute value of f of x minus f of c is less than epsilon, I want to solve this for f of c. That's what I care about. What do I get out of that? I get f of x minus epsilon is less than f of c is less than f of x plus epsilon. Oh wait, but that is now less than or equal to m plus epsilon. Where the last step holds since f of x is less than or equal to m. Good. So, thus, f of c, the bit that I actually care about, is less than m plus epsilon. And this is true for every epsilon bigger than 0, right? I started by considering any epsilon bigger than 0. Since f of c is less than m plus epsilon for every epsilon bigger than 0, we conclude that f of c is less than or equal to m. Great. Well, next, let's show that f of c is bigger than or equal to m. There will be like a silly case to deal with first, because let me tell you how the proof is going to go. So let's draw this picture. So there's c, which is the supremum of the set of all x's where f of x is less than m. If I look just a little bit to the right, this element is not in U. So that means that if there's this line at y equals m, the y value corresponding to this line will be above. So this point will have f of x bigger than m. Oh, wait, but similarly to before, this x value is really close to c, so this y value should be close to f of c. So f of c is really, really close to something that's bigger than m, so f of c should be bigger than or equal to m. But there's one problem. What if this c were actually equal to b? If that c were equal to b, then the reason this wasn't in U is because it's not even in the domain of f, so I can't take f of x in that case. So there's like this silly case. So let's deal with that silly case. If c is equal to b, then notice, by assumption, f of c is equal to f of b, and by assumption, f of b is bigger than or equal to m. So we get the desired result. F of c is bigger than or equal to m in the case that c is equal to b. If I can prove the result when c is less than b, then I will be happy. So let's assume that c is less than b. Just like what we just did, instead of proving the claim on the nose, I'm going to prove this. So here is my want to show. All right, well, let's do it. And this will feel very similar to what we just did. Let's consider any epsilon bigger than 0. Since f is continuous at c, it follows that there exists some delta corresponding to that epsilon, which satisfies that for, I want to give myself space, for all x in AB, the domain of the function, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. So that's just what you get out of the definition of continuity. So now I'm going to pick a carefully chosen x. I will take x to be the minimum, c plus the minimum of this delta over 2, and b minus c over 2. And let's do a few things. Let's first show that c is less than x. Well, why should c be less than x? I guess this minimum had better be bigger than 0. So that just means I need to know that those two things are bigger than 0. So let's do that. So let's see. By assumption, delta is bigger than 0, so delta over 2 is bigger than 0. Again, by assumption, at this point, b is bigger than c, there's the assumption. So b minus c over 2 is bigger than 0. Oh, great. And I think I actually, and I'm going to edit the notes, I think I want to do this next. Let's explain why x is less than b. And I'm going to, there's an error right now, but it will be fixed in the typeset notes that you'll be looking at. Well, let's do that. So notice the min of delta over 2 and b minus c over 2, that quantity is certainly less than or equal to b minus c over 2. Thus, x, which is c plus the min of delta over 2 and b minus c over 2, is less than or equal to c plus b minus c over 2, which you can check that on your own, but that's probably something that you've checked enough times that it's just bombed into your head now. Well, wait, so that is now less than 2b over 2, which is equal to b, since b is greater than c. Oh, neat. So this x value is actually less than b. And you know what? Let's go ahead and check this also. Absolute value of x minus c is less than delta, though that, again, is, like, pretty obvious. So right now, I certainly have c is less than x, because x is c plus something positive. That, in turn, is less than or equal to c plus delta over 2, which is less than c plus delta. So as c is less than x is less than c plus delta, it follows that the absolute value of x minus c is less than delta. Because of that, I think all of this will be moved up to. Theorem 3.1.4 concludes that the absolute value of f of x minus f of c is less than epsilon. And notice, to do that, it was important, though I didn't say it explicitly, that x be in the domain of consideration, the interval from a to b. Cool. So there's that. So let's start. I know it feels out of order, but it will feel in the right order if you stare at the notes that'll be online. So let's take c to be the supremum of u. So wait, no, we've already did that. Because c is in the supremum of u, could x be in u? Well, no, right? Since, that's weird. Since x is greater than c, equal to the supremum of u, x itself is not in u. So, what inequality can you conclude? Well, here I'm going to use this fact quite a bit. So let's see, since x is in AB, the fact that x is not in U implies, well, remember the definition of U. Let's even scroll up to remind ourselves the definition of U. U is the set of all x's with f of x less than or equal to m. So using that, the fact that x is not in U implies that f of x must be bigger than m. Alright, so I know there's a lot of scrambled stuff here, but the two things that I will need to now show that f of c is bigger than m plus epsilon is this and this. And it'll be basically the same as what we did previously in the previous claim. All right, so let's see. Because absolute value of f of x minus f of c is less than epsilon, I certainly get that f of x minus epsilon, is less than f of c. And that's all I'll need. I know there's more that I really know, but that's good enough. Because f of x is bigger than m, we get m minus epsilon less than f of x minus epsilon less than f of c. So m minus epsilon is less than f of c. Now we prove that for every epsilon bigger than 0. So I've proven f of c is greater than m minus epsilon for every epsilon bigger than 0. From that, I conclude that f of c is bigger than or equal to m. So let's just tie it up. Since we have proven that f of c is less than or equal to m, and f of c is bigger than or equal to m, we conclude that f of c is actually equal to m, and that completes the proof. So you can stop right here if you want to, but I think I want to talk you through one last application, which will be closely related to the homework. So I think I'm even going to talk through the proof of this proposition. It isn't one of the propositions that I'll grade, but let's do it. So if f from R squared is continuous, and the image of f has no upper bound and has no lower bound, then f is a surjection. So let's write down the assumptions. So let's let f from R to R be continuous. And let's let the image of f, so that's f of R, be unbounded above and below. And I think I'll go off to the side to say the want to show. I want to show f is onto, or as a surjection, pick which one you prefer. What does it mean to be onto, or if you prefer a surjection? It means that for every, let's call it m, in R, there exists a c in R such that f of c equals m. That's what we need to show. So we know what the first thing that we're going to do will be. We'll need to consider any m in R. We will then want to show that there exists a c in R with f of c equals m. Well, this is an application of the intermediate value theorem. So if instead of proving that, instead let's try to do something that has to do with the IVT. Instead, let's show that there exists some inputs a and b in R such that f of a less than or equal to m less than or equal to f of b. We can do that. If we can do this, then by the IVT, there exists a c between a and b such that f of c equals m and will be done. Well, why should this exist? And notice we haven't used an assumption yet. We haven't actually used the assumption that that the image of f is not bounded above and is not bounded below. Let's see, this m, is that m an upper bound on the image of f? It's not. So, since that m is not an upper bound on the image of f, how are you? It follows that there must exist some output, some f of b, with m less than f of b. Oh, well, that'll just do it. So I think I'm ready to actually start writing the proof. So we want to show that this f is surjective, so let's consider any element of the codomain. Let's consider any m in R. Since f of R is not bounded above / below, m is not an upper nor is it a lower bound on f of R. What does it mean to not be an upper bound or not be a lower bound? Thus, there exists some, I don't know, let's give them names that have to do with y's because they're outputs. There exists some y1 and y2 in f of R such that y1 is less than m is less than y2. So because y1 and y2 are in f of R, there exists some a and b in R such that f of a is equal to y1 and f of b is equal to y2. Thus, f of a is less than m is less than f of b. Oh, cool. Now I'm set up to use the IVT. Since f is continuous, the IVT now concludes that for some c between a and b, and notice I'm saying between a and b instead of in the interval a comma b, because I don't know if a is bigger than b or b is bigger than a. So I'm going to avoid making that mistake by just saying between, such that f of c equals m. Well, now let's summarize. Thus, for any m in R, we have exhibited some c in R such that f of c equals m. We conclude that f is onto. Wonderful. Well, as you're going through the homework associated with this section, I hope that viewing this is useful. And I apologize for uploading this as a single hour-long video. There wasn't really a natural place to break it this time. Anyway, I hope that you enjoyed. I hope that you're enjoying social distancing if that's possible. I'll talk to you later.